and then all you do is just put your drink down on the bar and you leave it alone. I'm not sure you expected that to happen, and neither did I. So let's try and explain what's happening. Electric fields apply forces to charges. Why does putting two transparent things on top of each other do something so strange when you turn it through 90 degrees? Welcome back, and I've got another fun and exciting experiment for you today. What we're going to be looking at is the national grid and those high voltage power lines and why we have to transmit electricity at such a high voltage. So you'll notice that Laika the space dog's not with us again today. She's off on another one of her world travels, and more of that at the end of the video. So, I'm sure you've all seen those high voltage power lines that are carried by those tall metal towers, and you know never ever to interfere with them. The voltages on them are absolutely lethal. But what I want to show you today is an experiment to try and explain why would you ever want to go to all the trouble of transmitting electricity at such a high voltage. So I've got a model here of the power lines that you might see outside on the pylons. It's not an easy one to film, so bear with me. This end, this power supply, represents the power station. And at this end, we've got the homes and houses and towns, etc. So what I've done is I've connected the power supply directly to these cables at the back here and to the house at this end. So there's nothing in the way, but what I can show is that the electricity is being generated from the power station. So those are the lights in the power station. Current travels in these wires and reaches the homes at the end. But I think you'll notice that the light is really, really dim. What's happening is we're getting a bit of a loss on these cables. So that's no good, because imagine if they were much, much longer. Now, one or two of you might say, well, you've connected it to DC. Okay, well, let's connect it to AC then. So here we go. Disconnect from the DC terminals. And as power stations do actually generate electricity with AC, let's see what happens. Well, I think you'll agree, I'll turn it up even further, that it's absolutely hopeless. That we can't seem to get electrical energy from the power station to the houses at this end by just coming along normal conducting wire. Okay, we've got to do something else. So as you can see, transmitting electricity with AC or DC at low voltages, we're using about 20 volts here, is useless. Okay, the energy doesn't get from the power station to the homes at all well. So what we're going to do is change things. And if you remember, the pylons carry very, very high voltage lines. That's the hint to what we're going to do. We're going to take the electricity from the power station and massively multiply up its voltage. We're going to step up the voltage. And then at the other end, we're going to step down the voltage. And to do this, we're going to have to use transformers. So let's set this up using the transformers, and bear with me, I'm going to do some slightly strange things to begin with. So I'll turn the power supply down, I'll connect to the DC terminals on the power supply, so that's direct current. And what I'm going to do now is take the electricity from the power station and plug it into the station transformer. And then the electricity will travel down these wires. I'll just remove this lamp for a minute. Okay, that won't affect anything. And I'm now going to connect the homes into a transformer at the other end. Okay, so let's turn on the power supply and see what happens. So up goes the voltage on the power supply. You can actually hear the AC buzzing there maybe. And nothing at the homes at the other end. So we've made a mistake here, and there's one change I need to make it work really well. So let's ever so slightly change our setup, and I hope some of you realised the mistake that I intentionally made there. Let's connect to the power station and make sure that our power station generates with AC electricity. This is electricity that's going on, off, okay? I've purposefully used green coloured wires because I don't want you thinking about plus and minus here. We're going to go from the power station and show that it's working with the lights here into a step-up transformer that's going to massively multiply up the voltage. We're going to travel along our cables and get to the other end with a step-down transformer, and that's going to reduce the voltage so we can use that electricity safely at home. So here we go. Let's turn up the power station, and you'll see the lights come on in the power station, and you'll see the lights come on in the homes as well. Now you might say, okay, well, that's not as bright as that one. Yeah, I agree, but it isn't as dim as it was before with low voltage DC and AC. And the other bit I wanted to show you was this little box here. There's nothing clever going on here. There's just some connections to these power lines in that box. Now, we've stepped up the voltage here to a very, very high voltage. So the technician has covered those joints with a box for health and safety reasons. And I had them put this in when I arrived at the school. I said, but if there's a very high voltage on those lines, how do you prove that to pupils without getting them to touch it and getting zapped? Get a mains bulb and put it in. So there we go. So this is a 240 volt bulb. There's the proof that the voltage on these transmission lines, the ones that would be up on the pylons, is extremely high. We've used the step-up transformer to multiply up the voltage on the power lines. Now, there's some real history in this experiment that you might want to go into by Googling it, but I'll do just a little bit of detail. There was a bit of a battle going on when this sort of system was first invented between Edison, the light bulb chap, who was keen on DC transmission, and I've shown you that that's not really very effective. You have to have the power station very close to the houses, otherwise you lose a lot of energy. And Tesla, who worked for Westinghouse, who realised that AC was the way to go. The thing, though, about the AC is that if you're going to transmit electricity over large distances, you need to step up the voltage. And the genius work of Tesla was to realise you needed transformers. So I've got a transformer here, and it has coils of wire in the primary, in the input stage, that are 20 times less than the coils on the output stage. So it takes in a low voltage, like 10 volts, and times it by 20 to give us about 200 volts. But at the other end, I've got the same transformer reversed, so I've got coils going from 20 lots down to 1 lot, that's the ratio, so I'm stepping down the voltage. So there are 200 times more coils on this side of the transformer than on the secondary. And if I take our 200 volts and step it down 20 times, I get 10 volts at this end. So our little school lamps work well. Now, the final bit on this one is transformers use changing magnetic fields to work. And maybe that's the topic of another video. So, do you remember when I connected DC? There's no changing magnetic field, so the transformers don't work. So you have to have changing current, you have to have AC to make a transformer work. So we've got all the components here now for a transmission line. We've got an AC power station, a step-up transformer, our power lines, and a step-down transformer at the other end. So all I've got left to do is to try and explain to you why do we have to transmit at such a high voltage. So you know that the pylons of the national grid carry cables with extremely high voltages on them. Some of them are up to 440,000 volts. So I need to account now for why we have to transmit electricity at such high voltages. Well, if you remember when we used AC or DC on these power lines and we transmitted at a low voltage, to get the power to this end, power to the houses is volts times amps. So if we've got a low voltage and a high power, we're going to have lots of amps, lots of current. So Tesla's genius was to say, well, if we've got lots of current, the cables are going to have to be thick and they're going to get hot and lose lots of energy. So why don't we step up the voltage, and that will have the effect of reducing the current by the same factor. So if we step up the voltage 10,000 times, the current flowing in the cables will be 10,000 times less, and they won't get as hot. Now, you can only step up voltage and step it down with transformers, and you have to use AC. But there's one other clever thing about why we want to reduce the current in the cables as much as we can. So I said to you that current is not a good thing in national grid cables. Current causes ohmic heating because the cables have resistance. It's a good thing in a toaster. You pass a lot of current through the elements in a toaster or a hairdryer and they glow bright red. They have resistance and they give out energy in the form of heat. But we don't want to heat up the cows and the sheep and the horses in the fields under the national grid, so we're going to keep the current really low. But I did mention there was something else going on, and this is really clever. The heating effect on the cables is proportional to, depends upon, not the current, but the current squared. So have a think about that. If you have more and more buildings taking electricity at this end, if the current in the cables, let's say doubles, becomes twice as large because they're drawing twice as much power, the losses in the cable will be proportional to that current squared, I squared. So twice the current, twice the amps, 4 times the power loss in the cables. They're going to get really warm and we're not going to get much electrical energy at the far end. Now imagine if you were going to draw 4 times as much current. Well, 4 squared is 16, so you would lose huge amounts of energy in the cables. So, the thing with the national grid that's so clever is keep the current low as you can, because the loss depends on the square of the current, and to compensate, step the voltage up. So, we can now understand why we have to transmit electricity at such high voltages. It's an attempt to keep the current low and to keep the losses on the cables between the power station and the homes as low as possible. So I hope you now have a really good understanding of why the national grid transmits power to homes and cities on cables at very high voltages that have to be kept well out of the way of us walking around on the ground. You should now have a bit of an understanding of why we have to use transformers to step up and step down, and why we have to generate with AC electricity, and our devices at home use AC electricity as well, because transformers only work with AC. So I'll be doing another video soon, and I look forward to seeing you then.